So this is question 5 from the 2022 Matt. Alice is participating in a TV game show. N distinct items are placed behind N closed doors. The game proceeds as follows. Alice picks the door I, which is opened, and the item behind it is revealed. Then the door is shut again, and the host secretly swaps the item behind door I with the item behind one of the neighbouring doors, I-1 or I+1. If Alice picks door 1, the host has to swap the item with the one behind door 2. Similarly, if Alice picks door N, the host has to swap the item with the one behind door N-1. Alice then gets to pick any door again, and the process repeats for a certain fixed number of rounds. At the end of the game, Alice wins all the items that were revealed. Right. As a concrete example, suppose N equals 3. If the original items behind the 3 doors were A1, A2, A3, then if Alex picks door 2, the arrangement after the host has swapped the items could be A2, A1, A3, so it's swapped A1 and A2, or A1, A3, A2, so it swapped A2 and A3. So if Alice was allowed to pick twice, had she chosen door 2 followed by door 1, in the former case, she would only get item A2, and in the latter, she'd get A2 and A1. Yeah, okay, this is all fine. Alice's aim is to find a sequence of door choices that guarantee her winning a large number of items, no matter how many swaps are performed. Right. N is 13, so we've got 13 doors, give an increasing sequence of length 7 of distinct doors that Alice can pick that guarantees she wins 7 items. Okay, well 7 is one more than half of N, so I'm assuming we're picking alternate doors here. So if we pick door 1, that doesn't affect door 3. So we can go 1 and 3, we can go 5 because that would be unaffected, 7 would be unaffected, and 9 and 11 and 13. So that's 7 doors, none of which affect any of the others because they only affect neighbouring doors. So yeah, we're fine by doing that. Part 2, for any N in the form 2k plus 1, give a strategy to pick an increasing sequence of k plus 1 distinct doors that Alice can use to guarantee she wins k plus 1 items. This is what I've just done, isn't it? And that's exactly the same question, is it not? Isn't it? 2k plus 1, so we've got k is 6, 13 doors. Yes, we're just doing the same thing. So we want to pick, briefly justify. Right, so we're just doing exactly what I've said. That's really weird. So 1, 3, 5, dot, 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 up to what we got. 2k plus 1 is the end one. So why is this okay? Because only neighbouring doors are affected when a door is chosen. Therefore, we will, let's say, well, let's go for open alternate doors to reveal initial items behind those doors. That's kind of weird that they've answered that for part 2. I mean, what else were people thinking when they were answering part 1? I mean, maybe there's another way to think about the first part, but essentially you're doing part 2 in order to achieve part 1. So a little bit strange, but still. Part 3, for N is 13, give a sequence of length 10 of doors that Alice can pick that guarantees she wins 10 items. Right, sequence of length 10, right? It's not an increase in sequence this time, and it's not distinct doors. So they've removed increasing and distinct from what we had in the previous one, and now we can get up to 10 on this. So how does that work? Because, yeah, how does that work? Well, I mean, if we do 1 twice, we're okay. If we do 1, 1, because that would be essentially opening the first 2 doors. if we've done that. So that's okay. We could have the same at the other end for 13. So we'll have 13, 13 at the other end. So that's given us 4 items and 4 out of our 10. So if we're doing pairs, if we could have 3 more pairs, so what would that be? 4, 7, and 9. So why is it working out that way? Then, yeah, because if we're hitting them twice, if you hit you hit an unmodified, so we do 4, 4, 7, 7, and that wouldn't be 9, would it? It'd be 10, 10, 10. Yeah, if you've got a block of 3 that hasn't been touched and you hit the middle one twice, then you're going to get 2 of those 3. Because if you've got, say, A, B, C, so we open that one, you get whatever's behind that door, and it's going to swap in either A or C in there, and then you open it again and you'll get the other one. It doesn't matter which way B has moved, you're going to get 2 out of 3 of every set of 3. So that's that bit. And now, yeah, part 4, they're asking us to explain it. So, yeah, how are we going to do? So we want to say for part 4, so starting with door 1, yeah, so we want to do, well, we want to open every third one twice. Starting with door 1, so open door 1 twice, which gets us doors 1 and 2, 1 and 2, original items. And then we want to say that we're going to open every third door twice. So yeah, we're going to get 1, 1, 4, 4, 7, 7, dot, 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 up to 3k plus 1, 3k plus 1. And this works because for every isolated, let's say isolated set of 3 doors, opening the middle door twice in succession will reveal 2 different items. Will reveal 2 different items. Okay, so this is going along fine, but I don't feel as though they've really got into their stride of asking horrible stuff yet. So still got 4 more parts to this, so it could go horribly wrong. For Ennie's 3, give a sequence of length 3 of doors that Alice can pick that guarantee she wins all items. Right, so we do door 1 twice and then door 3, because we know door 1 twice gives us 1 and 2. So that's okay. And for Ennie's 5, give a sequence of lengths 5 of doors that guarantee she wins all items. Right, so 1, 1, 5, 5, 3. Right, that's fine, because again, we've already been talking about these things. If you do the first one and the last one, then you get the first 2 and the last 2, and then we do the one that's in the middle. Okay, part 6. Ennie's 13, give a sequence of length 11 of doors that Alice can pick that guarantees she wins 11 items. Wow. Okay. Right, that sounds different. I thought we'd maxed out on 10, but clearly not. So we've only got 2 things here that we're not going to be able to get out of all 13. Wowzers. Right, so how is this going to work? Right, this is not what I was expecting. So let's put numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oops, 12, 13. So we've got 2 of them that are missing. So it must be 1 in either half. So we must end up getting 7, because this has got to be symmetrical. there's nothing about starting at one end rather than the other. If it's got to be symmetrical, we've got to have one of them from 1 to 6 and one of them from 8 to 13. But it's not going to be 1 and 2 because we know we can just pick those ones off. I mean, surely that has got to be part of this sequence. We don't really have any choice, do we, than to do that as part of the sequence. So let's say we're going to start off 1, 1 and 13, 13. That just seems safe. So we've done both of those and both of those. We know we're going to end up doing 7, but now I've got this block of 4 and I've got this block of 4, providing we don't do anything that disrupts the 7. We could just pick the 7. We could just throw that 7 in, but then we've got these blocks of 4. So how would that work? How would that work? Yeah, if we put a 7 in, well, we've got a block of 3. Well, we can't do anything with the. Could we do 3, 4, 5? What if we did 3, 4, 5? If we did 4, because we did 4 a couple of times before. No, I don't know how that's going to work. Yeah, I'm not quite seeing this at the moment as to where we're going to go. So say we did 7 at the end. We need to then pick up 3 out of these 4. We know we can do 2 out of every block of 3. So block of 3, block of 3, block of 3 is what we had before. So we can't be doing those same blocks of 3 because that's what we did in the previous one. We had a 3, 4, 5 and took 2 of those, and then 2 out of 6, 7 and 8, and then 2 out of 9, 10 and 11. So it's going to have to be the different set of 3 to what we had before. So it's going to have to be that block and that block. So we can take 2 out of those. Oh yeah, but neither of those are moving 3, 7 or 11. So providing we do 3, 7 and 11 at the end, then we're okay. Right, okay, so that's fine. So we can then do 5 and 5, because that will give us 2 out of 4, 5, 6. We do 9 and 9, because that'll give us 2 out of 8, 9 and 10. But 3, 7 and 11, none of them have then moved. So we then do 3, 7 and 11 to finish off. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, that's quite sneaky. Yeah, that is quite sneaky. So that's dealt with that one. And we don't have to give a description. Oh, okay, we do have to give a description. For any n, 4k plus 1, yeah, this is what we're just saying here. Right, so we need to break up. We're doing every 4th one now, aren't we? We're doing twice. And then we're doing the odd ones. So what is our strategy for this then? We're doing 1, 1, 1, 1, 5, 5, and 9, 9, 13, 13. So we're doing that. And then we're doing afterwards, we're doing 3, 7, 11. So that's just rearranging these ones to put them in a bit of a sequence. So 1, 1, 5, 5, and then that'll be all the way up to, so dot, 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 4k plus 1, and then 4k plus 1. And then we do what we're doing for these ones. So that is 4k minus 1. No, not 4k minus 1. Well, up to 4k minus 1 is what we'll have at the end. That is 4k minus 1. That is just counting in threes. So we then go 3, 7, dot, 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 up to 4k minus 1. So yeah, that works, doesn't it? So it's like we've got these two sequences matched together, like appended to each other. That's the word I'm looking for, appended. So we count up in 4s up to 4k plus 1, starting at 1, and then we count up in 4s to 4k minus 1, starting at 3. So yeah, start at 1, counting up in 4s to 4k plus 1, open each door twice, and then start at 3, count up in 4s 2, 4k minus 1, open each door once. Right, okay, and we have to justify this in some way. So what are we getting here then? We're getting 2 in the first 2 doors, 2 in the last 2 doors. So we've got 2 plus 2. So that's first 2, last 2. Then we've got block of 4, 1 in the middle, block of 4. So we're going to have the 1 in the middle. Are we always having 1 in the middle? Do we always get... Yeah, this is an odd number. So we're always going to get 1 in the middle. 1. So that is first 2, last 2, middle. And then every block of 4, we're getting 3 in. 3 in each block of 4. Okay, so, well, this is a block of 4, first 2, last 2, but we're actually getting all 4, not 3 in that one. So we've got k blocks of 4. So therefore, our total is we're going to have 3 lots of k, because we're getting 3 in every block of 4, but that block of 4 we get an extra 1, plus we got the 1 in the middle. 3k plus 2, which is what we want. Right, onwards to the last part. For any 6, there is a sequence. Is there a sequence of any length of doors that Alice can choose that will guarantee that she wins all 6 answers? So justify your answer. Guarantee it. So, right. We might have a few weird permutations on this one. I don't know. I mean, that seems like a lot to be able to do. 1, 2, 3, 4, 5, 6. So if we did our usual starting 1, 1, 6, 6, that takes out 1, 2, 5, and 6. But then we hit 3 and we don't know if 2 has moved in or 4 has moved in. So is that the one that we want or the one that we don't want? So as soon as you hit 3, then 4 could be going to the 3 door. It could be staying where it is. And then can you do anything about that? I mean, if you hit it again, well, you could just keep saying the same thing. We got, I mean, it's symmetry, so it doesn't matter if I'm thinking about 3 or 4, it's the same thing. How do we guarantee we're going to get the one behind those doors? Yeah, you hit 3. Even if we keep on hitting 3, it doesn't really matter, does it? Because 4 could always go where we don't want it to be. I'm just thinking, justify your answer. It guarantees that it's going to win. I mean, how can we guarantee that it's going to win? Or say that it definitely can't? We need there to always be a choice, always be an unknown, which means there's always a possibility that it can go wrong. But how on earth do I put that into words? So, right, let's start off by saying 1, 2, 5, 6 are easily, I don't know, what's the word, detective, opened, 1, let's say 1, because that's what they're doing. She's trying to win these items. So we could say 1, 1, 6, 6. For 3, for door 3, and therefore door 4 by symmetry, so at least we don't have to talk about one door, then every time 3 is selected, 4 could move to 3 or stay at 4. Therefore, not guaranteed. Not sure this is enough. Is this enough of an answer to get 3 and 4? Is that convincing enough, or do I need to say a little bit more on this? I mean, if it's guaranteed that you can get it, I mean, this might be a different way of looking at it. If you've got a sequence, if you've got some strategy where Alice can guarantee she's going to get every single item, then there has to be nothing that the host can do about it. maybe that's another way of going about it. So maybe I could stick that in. So if Alice is guaranteed to win all, then host cannot foil it. Host cannot foil the method. So he could know in advance exactly what it is that she's doing. I mean, that's another way of putting it. But then, actually, that's exactly the same thing, isn't it? I don't really know that there is much more to say on this. The host cannot foil the method. So if he'd know in advance, he'd be able to say what she's doing next. Yeah. So he would effectively know. Yeah, this works out better. Effectively know Alice's next choice. Therefore, he can move the item 4 to wherever she isn't picking next. Yeah, I think that's a better way of putting it. It's essentially amounts to the same thing. So what I'm getting at here, if you've got a foolproof method, then you must be able to say in advance, right, I'm going to do such and such, whatever it may be, 1 1 6 6 3 4. That's what I'm going to do. If that's guaranteed to work, then it doesn't matter if the host knows in advance, because it's only guaranteed if there's nothing that the host can do to stop it. So once she's done 1 1 6 6, you think, okay, fine, that's covered those two and those two. Then opens 3, which covers that one. But the host knows that she's going to pick 4 next, so he'll just stick 4 into the 3 door, in which case she'll then miss it. Now, if she was going 3 3 at the end, he'll just leave it where it is. And you could take this sequence on as long as you like. Every time she hits a 3, he knows what she's going to pick next. So he either moves the 4 or he doesn't. Right, yes, I'm happier with that as an explanation. So that was quite a tricky bit at the end. Yeah, that was a weird sort of question, that one, because the early bits weren't really that bad. I mean, these coming up with these initial sequences of getting the length 7 and length 10 weren't that bad. And it was a bit odd that we then had to describe the strategy afterwards, when clearly we'd done that beforehand, but still, that was okay. And then these part 5 ones were easy. Part 6 was tricky, but it was easier because, again, we had looked at the earlier part. So if we had already taken a set of 3, which was 3 4 5, well, we're not doing that again. It's going to have to be 4 5 6. Otherwise, we're just repeating part 3 or 4, whatever it was. So that helped with that, which made that part fine, because again we were just justifying it. And the last part was definitely the most difficult. But yeah, it was quite a meaty question, all in all, but a nice one, quite interesting, different to the usual sort of question 5s that they've had in the past.